Page 2, I'll probably just be needing my periodic table handy. Page 2 is about balancing equations, and it's saying balancing them and including a particle diagram. I don't care if you balance them and then draw the particle diagram, or if you use the particle diagram to balance them. I'm going to do that method because there's more just plain balancing later. So I'm trying to understand what is represented by an NO. They're talking about a particle, nitrogen, tied to another one, oxygen. There's a molecule. It's going to be added to an O2. That's an oxygen tied to an oxygen. And it's going to make an NO2. Now I could put this in a straight line, NOO, but I'm envisioning an N in the middle and a couple of O's on on each side. So if I really look this over, you really just can't have 1, 2, 3 oxygen, and then when you're all done, only have 1, 2 of the oxygen. Things just can't disappear. So you can't start out with those ingredients, which they're saying makes it, and end up with just one NO2. So what that tells me is you got to at least have one more NO2. So I'm going to draw another NO2, just like I had over here. I'm not sure if I'll be done, but I'm going to start with that. Okay, now we've got another situation. You can't start off with just one of these and end up with 2 of these. So apparently we had to have more of the ingredients at the beginning, NOs. So I come over here and I draw an N, and I'm tied to an O again, because that's exactly what this is saying, an N tied to an O. Now when I count it up, I have 1, 2 of those, 1, 2 of those. I have 1, 2, 3, 4 of those. 1, 2, 3, 4 of those. That's a balanced equation. So how many did I make? How many NOs did I make? 1, 2, 2 NOs. I only made one O2. That's just an O2 right there, just one of them. I don't need that. I can put it there. I don't need it though. And finally I made 1, 2 NO2s. So you don't have to write all these little numbers. I'm just trying to go back through the process of how could we balance this using diagrams. The next one, I need an Fe, a Cl tied to a Cl, chlorine, and then an FeCl3. I'm envisioning the Fe in the middle, flanked by 3 chlorines. There's no way you can start off with 2 chlorines and end up with 3. So apparently we're going to need more chlorines. So but they only come in pairs, so I draw another chlorine tied to another chlorine. Well, there's no way we can start off with 4 chlorines and end up with 3. So I'm apparently going to need another one of these Fe, Cl, 3s. Now what do I have? Now I have 6 chlorines on this side and only 4 on this side. So I come back and make another Cl. There's 6 and 6. Everything matches except the amount of Fe's, which come separate. They're not joined together. Apparently it's going to take 2 of these, 3 of these, and you'll get 2 of these. So it's using a diagram to see how to balance a reaction. You draw just the shapes that they say to, and you keep adding until you have the same amount of every atom that there is. Okay, so balancing more the traditional way. The traditional way, probably more likely to make some T-charts. Here is a combustion reaction. Combustion reactions, you have to count C's, H's, and O's. My recommendation for every combustion is to count them in that order. First things first, we have to count up how many are on the reactant side, how many are on the product side. That little arrow tells me reactant versus product. I see 3 carbons, 8 hydrogens, and 2 oxygens on this side. On the product side, I see 1 carbon, 2 plus 1 is 3 oxygens, and 2 hydrogens. When I'm balancing these, I'm going to start with the C's. We have 3 C's over here. I'm going to need a 3 there. Next thing I'm going to do is I'm going to go to the H's, and I'm not even going to recount. I have 8 H's over there. I need 8 over there. I need a 4 there to change that into 8. That fix that to 3. Now count your oxygens. 3 times 2 is 6, plus 4 more equals 10. I have 10 oxygens on this side. That says, how do I get 10 oxygens on this side? Simply put a 5 there. That's balanced. Suggestion on this one, when you're counting these up, I would suggest counting SRs, OHs, even though this looks like we should have O's and H's separated, keep them together. When you have a polyatomic ion that the polyatomic ion looks the same on this side and this side, don't make it more complicated. Count them as a single entity. Count up each side. I see 1 of these, 2 of these, 1 of these, 3 of these. But on this side, I see 1 of these, 2 of these, 1 of these, and 3 of these. Pick something that doesn't match, figure out a great way to fix it. I see this classic 2-3-3-2 dilemma. Usually when that happens, you need to figure out a way to make 6 on each side. So when I'm looking at the fact that there's 2 hydroxides on this side, but 3 on this side, I'll probably need to triple this and double this. You triple that side. When we recount the triple, we're going to have 6 of these, but now I have 3 of those. So you got to recount everything when you put a coefficient in front of it. On this side, now I have 3 times 2, I have 6 H's, 6 OH's, but now I also have 2 irons. Another thing I need to probably fix, the same problem with my chlorines, a 3, 2, I'm probably going to have to triple, double to make 6 on each side. So if I put a 2 here to get 6, that fixes this to 2. And if I put a 3 here to make 6 chlorines, that fixes the strontium to be 3. That is now a balanced reaction. 3, 2, 3, 2. Moving on down. Another combustion. Combustions are characterized by having C's, H's, and O's. And one of your products is water and the other one's either carbon dioxide or carbon monoxide. Count it up. If you have 6, 6, and 2 versus 1, 2, 2 plus 1 is 3, save your oxygens for last. First, fix your carbons. Put a 6 there. That fixes your carbon. Don't even recount yet because you're going to change it again. Then fix your hydrogens. 6 versus 2, I got to triple this to get a 6 there. Now recount your oxygens. 6 times 2 is 12 oxygens plus 3 more is 15 oxygens now. Uh-oh, what can I write there that would make my grand total of oxygens 15? Well, in this case, the only thing I could put 7.5 there, and that would make this perfectly balanced, except it's not quite legal. So when you do something like that, there's one method of doing that. When you do something, even though it's balanced, we need to just scale everything up. Multiply everything by 2 so everything's an integer. Instead of 1 of these, let's make 2 of these. Instead of 7.5 of these, it'll be 15. Instead of 6 of these, times 2 is 12. Instead of 3 of these, you're going to get 6. Next one. At the time we didn't know this, but this is a acid. Now we know this is an acid and this is a base. And of course this is water and this is a salt. At the time we just said let's balance that equation. We still can use some of the same principles though. I'm going to be counting H's, SO4s, I'm not going to break that up because the SO4 looks the same on this side, BAs, and OHs. It's easy to count the left side. 2 of these, 1 of these, 1 of these, 2 of these. The right side's a little more complicated unless I do this. If I count this as H's tied to OH's, I have 1 of these, 1 of these, 1 of these, Ba, or what SO4, and one of these. So what doesn't fit? The only thing that doesn't match then is the HOH, the H's and the OH's on the right side. They're linked together. Put a 2 there. That'll fix this to 2, this to 2. That one is now balanced. That's an acid-base neutralization. We just didn't know that at the time. Another one of these. When we have C's, H's, and O's, I recommend doing it in that order. Quickly, this is another combustion, a complete combustion. 2, 2, and 2 versus 1, 3, and 2. First, fix your C's by putting a 2 there. Then your H's already match. But now we got to recount how many oxygens. 4 plus 1 is now 5. Here's another one of them cases where 2 versus 5, we have odd, even, or even, odd. If your oxygens are odd, even at the end, you either could write 2.5 there to make that 5, or the other thing is just, if it's odd, even, you can try to remember, double everything and then fix the oxygens. So double this, 1 becomes 2. Double this, 2 becomes 4. Double this, 1 becomes 2. And now when you recount your oxygens, we have 8 plus 2 is 10 oxygens on this side. A 5 there will fix it. I could have written 2.5 and then did the same thing, doubled everything, get the same result. Next ones are word problems. So it's probably going to require a little bit more of some checking some periodic table. Iron burns in air. Find iron. There it is. Its symbol is Fe. Fe. Burns in air. That means that it's mixing with burning, iron, air, mixing with oxygen in air. We just had to know that, and there's the hint, but we should know that, to form a black solid. What's the name of that black solid? Iron 3 oxide. Need to use my naming rules to figure out its formula. I could go back and kind of look that idea through. Iron 3 oxide is the iron with a +3 tied to oxygen with a -2, because all oxygens have a -2. Crisscross 2 of those, 3 of those. The other product is going to be Fe2O3. Is that balanced? No. If you have 2 oxygens on this side, okay. Could either think, I'm just going to do it this way. If I have 2 oxygens on this side, it seems like I need 2 irons on this side. But I have the classic 3-2 dilemma. I probably should have started with the oxygens. If I have the classic 3-2 problem, I probably need to double this to get 6 oxygens and triple this. That means that I have 4 irons over there. This was not correct. 4 Fe. Just a different method of balancing a reaction. Last one, magnesium hydroxide. I have to look and find magnesium. That's a metal. And that's magnesium has a +2 charge. It's tied up to a hydroxide with a -1 charge. Crisscross, that's MgOH, has to be taken twice in parentheses. Reacts with nitric acid. This is before you knew how to do acid, so they told you that it's HNO3 to form water. You know that. It's H2O. Or do you? I'd write it as HOH. When we're doing an acid-base neutralization, now we know that HOH is probably the way to go. Finally, it's going to be magnesium nitrate. Magnesium has a +2. Nitrate is a -1. That is not a match made in heaven. It's going to take 2 of those to balance off just 1 of those. Magnesium, just 1. Nitrate, 2 of those, so it's got to be in parentheses, taken twice. First step, just writing them. Ask yourself now, is this balanced? I don't think it is. If I'm going to balance this one, I'm going to count Mg's, OH's, H's, and NO3's. I'm not going to break it up into all the little parts. I'm just going to count it like this. 1 of these, 2 of these, 1 of these, 1 of these, versus 1H, 1 OH, 1 magnesium, and 2 nitrates. First thing glaring that I see, I'm going to save my H's and OH's till the end. These I'm going to save till the end. So first 2 fixture nitrates. How do you fix that? Well, we need a coefficient where the nitrates are. We're going to need 2 of those. That changes this to 2, but it also changed this to 2. That's kind of good because now these are the only things that don't match. We need twice as many of these to make 2 and 2.